much for the introduction. Is it take file? How the oh yeah. Okay. This is a topic called today. I'm going to talk about the multi-modal problem and about parallel simulation technique. And after that, I'm going to talk about experiments. Okay. The multi-robot routine is defined by that we have homogeneous agents as well as targets that are initially allocated in the robot. Then the condition that each target must be corrected by an agent and must be delivered to its destination by one agent. And for example, if we have we have two agents here and three targets, and in this case, agent A1 corrects the target this target and then delivers to its destination, and this agent corrects two targets and then delivers them to their destinations. And so this is a kind of extension to the existing setting for the multi-robot routine problem. And but one more important extension to this problem is that the travel distances are not known beforehand, which means that we have to actually calculate how long it's going to take from location to location and by performing some computation. And objective, and in this talk, I'm going to talk about two objectives. One is to try to minimize the maximum path cost of any single agent, which means that we want to reduce we want to minimize the response time for the slowest agent, such as for the search and rescue operation in a disaster situation. And the other one is to minimize the total path cost of all agents, which means that we want to reduce the energy cost for the agents, for energy efficiency. And this has been quite a representative domain, especially for studying multi-agent techniques. And the whole topic is about using the option-based approach in order to approximate the result of this problem. And let me move on my motivation for this problem. And typically speaking, multi-robot routing problem assumes that the distances between locations are pre-computed beforehand, which means that if we want to know the distance between locations, all we have to do is to look at the table, which can be easily done with an order of computation and cost. However, we consider the case where we need to calculate the distances on demand, which means that whenever we have target and agent, we don't know how much time it's going to take to pick up this time, for example. And we need to perform calculation, especially based on pathfinding parameters on the road. And typically speaking, for example, this is not an easy task, and it's computation, and it's non-negligible in terms of computational cost. Because, for example, in the OpenStreetMap of Dublin, we have like 300K nodes and 320K road segments. And on top of this search space, we have to find paths in order to calculate this question mark path in the location, in the distance. And assuming in this setting, and the current, what happened in the previous work is that only serial simulation performed, which means that we have, the simulations performed on one CPU core where agents are simulated sequentially. But on the other hand, we try to perform like a parallel simulation by using a set of set of machines where each agent corresponds to each CPU core, so that each agent can calculate the distance or location of demand in parallel. And by doing that, we reveal the fact that there's a even overhead, especially related to synchronization, which hasn't been considered in the previous work. And then after that, we present two simple approaches in order to resist such synchronization overhead, even in the sequential simulation, but which happens in parallel simulation. And let me explain how things are working in case of serial simulation, where we have only one CPU core to perform this, to run the algorithm or functions. And typically, to approximately solve multiple logic problem, we perform sequential single item function that consists of n rounds, where n is the number of targets. And what we do here is that in each round, basically each agent calculates the bit cost to bid on to bid one allocated target. Then we have two strategies for that. And in case of minimax, we try to calculate the minimum cost when we add a new unallocated target to the current shortest path cost. While in case of min-sum, we try to calculate the difference when we add a new target. And usually computing the shortest path cost itself is really hard. We take an approximative native approach in order to calculate that. Basically, based on like a simple TSP-based insertion-based heuristic, which try to insert one location to the current path to construct the difference. And in this talk, I assume that any pathfinding method is okay, but I assume that the pathfinding based on construction hierarchy, which is quite popular for finding paths on the roadmap, is used, and with some enhancements. And so, yeah, I will explain that one for details in the paper, but the point is that we have this kind of pathfinding procedure combined with TSP insertion-based heuristic in order to calculate the bid cost for each agent. And then after all the agents calculate the bids, what happens next is the server who does receive all the bids from all the agents, determine the winner by assigning one target to that winner. Then we keep doing as a repetition, and then once we finish n times, we are done, and we have a set of targets assigned to each agent. And this is how the sequential simulation with single item, sequential single item option works. However, when it comes to like a parallel simulation setting, the thing is that each agent can bid on one allocated target to the basic cost, but it's the same. However, we can work on that in parallel. So, which is a frame of the previous part that we can easily parallelize the algorithm, because each agent can use only like localized information on the other agent and then locally compute the bid cost. And however, here, because the server determines the winner after all the agents finish bidding, which means that agents that finished bidding must wait until the server receives the bids from all the agents and send out the winner to the agents. So that means that we have to synchronize, which is not considered in the simulation. And let me show you how this is a CPU problem when we have an algorithm that is combined with pathfinding procedure for locations. And in this case, we use like 40 agents shown in this line, and this is time. And the red line means that the agent is working, while this missing is that agent is sitting idle, doing nothing. So as you can see that we have a lot of synchronization over here. When we consider simulations, we consider running the option-based approach and the parallel simulations. So that means that this algorithm is not like easily parallelizable when it comes to like the setting where agents must be simultaneously. So, and to bypass, to alleviate this problem, I try to present two approaches. One is I call it broadcasting. And the idea is actually quite simple. Because the server collects all the bits from those agents, which means that the server keeps the current best bit in order to become the winner during each round. Then what broadcasting does is that whenever the server receives a better bit cost, the server just broadcasts that information to the agents, so that these agents that are currently calculating bit costs can stop earlier when these agents are proven to have no allocated target. They can't. If we have a situation that they can't, they just give up bidding. In this way, this approach tries to prune such space of pathfinding, finishing the bidding earlier and hopefully reducing the idle time. Of course, we have to incur more communications compared to the simple bidding strategy, and the original bidding algorithm. So there's a trade-off between the communication overhead between the server and the agent and the amount portion of the size space from the available using this. And currently, broadcasting has a parameter called K, which limits the number of times to broadcast agents. To the winner and to the current best bit information to the agents. And let me show you how it behaves when this approach is incorporated. Again, the graph is the same thing. Compared to the baseline, we have a better situation. But still, there are cases where the agents sit idle doing nothing. Therefore, I'd like to draw this from an approach called speculation. And in a way, it's not the idea to sit idle while after agents finish bidding. So rather than sitting idle, they just speculate for the next round. And there are several ways. The one way is that we just optimistically assume that the agent wins target, and then that agent is added to the current shopping path. And then based on that path, that agent try to speculate on the future and keeping with that. Another way to do that is like we pessimistically assume that agents always lose, and then finally to the next choice. And actually, in this talk, I'm going to show only the pessimistic speculation result, and this doesn't differ in terms of performance. There are similar performance I have taken between optimistic and pessimistic speculations. And the pros of this approach is that we can immediately use the speculated result if they are correct. And by doing that, the speculation attempts to reduce idle time of the agents. And also, actually, this one attempts to improve of the SPC calculation bound and the details are getting. Okay, and then by doing that, finally we get the data result in return to idle time for minimums. And most the agents are, I think, 85%. The number is pretty big. But yeah, and the agents start by their even if they don't have anything to give. But this is the case for minimums. However, for the case of mini-sum, we still have a lot of time. We improved the performance dramatically. But for the, especially when it comes to the ending stage, we still suffer from the idle time. The reason is that in the case of mini-sum, there are a few agents that take most of the targets, which increase the pass size. As a result, that agent becomes a bottleneck for cost calculation because it has to consider many combinations of paths to include. As a result, they have become a bottleneck and the other agents finish bidding until the end of the round. And in this way, they have nothing to do, and they have to, and this is the kind of thing we have to resolve when it comes to simulation approach and parallel simulation. Okay, so and other results related to this topic is that we actually measure the speed up by preparing the algorithm for sequential serial simulation, and also we implement the parallel simulation and measure the speed up in this way. Just measure the fraction. And okay, let me show you the speed up results. This is the case of minimums. And if we add broadcasting technique, we get a better speed up. And then adding speculation, the speculation has a higher impact, but by combining both, it's slightly more improved speed up, resulting in something like 18-fold speed up with in case of 40 agents. The 40 agents are running independently without computation, except between 0 and 0. And but for the case of mini-sum, the speed up value was lower. With 40 agents, even if we use both approaches, speculation and broadcasting, we have achieved something like 8-fold with 40 agents. The reason is again that some agents are taking time and resulting in causing the others to sit outside. So that is why we have a problem to scale up. Okay, so in conclusions, in my talk, we reviewed the hidden synchronization overhead for SSI option algorithm, and when they are combined with partial algorithm. And if we perform simulations under parallel simulation settings. Because of the fact that the big calculation overhead, computational overhead, big calculations are balanced among agents. And in order to bypass this problem, I presented two approaches, micro-casting and speculation, the other speculation. And the finding that combining both approaches improves the performance, but speculation seems to impact more on the performance. As a future work, one clear thing that we want to improve the parallel performance further, especially for mini-sum. And another thing is that there are many other building algorithms that perform more complicated computation, and we want to combine this kind of approach with more complicated building algorithms that returns better approximation rate to the solution. And of course, finally, there are cases where communication fails and communication failure may occur when we use robots. and we want to investigate this kind of scenario. Okay, that's all I have to say. Thank you very much.
So we have time for one or two questions.
Hi, it's more a clarification. I got a little bit lost at some point, but the impression I had is that this problem is actually quite similar to the die-or-write problem. It's somehow a classic online optimization problem. So my question is, why do you need to employ multi-agent-based solutions to solve this problem? What are you getting from this framework that you couldn't have in an optimization framework?
You mean that the question is what's the value of like applied, employing the auction-based approach?
Yeah, basically, why is it better to use multi-agent-based solutions rather than traditional online optimization solutions?
Yeah, I mean that in a way we can reduce the computational complexity if we distribute agents in a distributed setting, because we have considered we have only to consider smaller subset of the targets. But as I said, we have to consider more things than what is considered currently.
And do you have an idea about how much optimality are you losing? How much you're losing from the optimal? How far are you getting?
Oh, I see. I mean, there are theoretical results. I think I'm not sure of this setting, but when we have only to visit the target, I think the approximation factor for mean sums, I think a factor of 2. And for the other one, that was not good, 2 times M1, where I think getting the dark side. I don't remember the exact number for that approximation factor, but I think so. Yeah. So we have some theoretical results in the existing, result in the existing literature about the approximation.
Okay. Thank you very much. It's time for the next talk now. Okay, our next talk is multi-agent sensor data collection and phishing risk by Haddock and Holm, and Jack Adam will be in the talk.
All right, thank you. So I'd like to start out with a little clarification when I say multi-agent. What we really mean is a centralized solver in this case, so more of a multi-actuator type of problem. And as far as planning, we're talking about planning ahead of the problem. We're not looking right now at dynamic planning or changing environment active planning. So in a sense, it's anticipatory planning to deal with risk and how you can use the planning to anticipate and mitigate the risk. And I should also add that I'm not very close to the planning community, so I'm really presenting our problem with the hopes that I can get input on other ways to solve this problem, other ways to formalize this problem. Is it possible to find optimal solutions? These are a lot of the questions that I came here to have answered, and so I'm very open to input on how to do that. So definitely appreciate talking, certainly questions or after my talk. So I'm going to try to get a metaphorical example of the problem itself. So we have is a hunter in a village. His job is to go out and gather food for his village and return to the village with that food. If he does not return with the food, then there is no reward that is gained. And he basically needs to mitigate the risk in the environment as part of his plan to go out to those hunting locations to gather that food. Now, in the base case, there's no risk in the environment at all. And clearly, you just choose the shortest path to get all of the food from each of the locations and bring it back. We'll assume that there's no slowdown of the hunter for having to carry all that food. We'll assume he can hold it all on his path. It starts to get a little more interesting when we talk about having predators in the environment. Now, while they're located physically on this slide here, you can assume the predators are in unknown locations. There's just a general amount of risk of a predator finding you as you travel through the environment. And if they find you, they'll eat you, and anything you've gotten so far is lost, and you get zero reward for all of your troubles. And so it starts to get interesting because now the optimal path is not to get all of the food, but rather try to maximize the value of the food as opposed to the risk of losing both yourself and the food that you would have gathered so far. And so you now have a very interesting balancing problem that needs to be done. And now it's a little more dangerous. It's starting to become nighttime. Your path becomes even shorter. It's not worth traveling that amount of distance to get out that far and risk losing your life to get that reward. And so often when the risk is high, the best option is to choose a few number of tasks very close, complete them and get home. And then in the extreme case, where the night is dark and filled with terrors, your best plan is to not leave at all. Stay home and wait for the risk to pass because you're most likely not even survive trying to get anything. So applications for this, primarily I consider military applications. We have many unmanned vehicles. How do we plan for them to do collection of imagery and video in highly contested environments? There may be adversaries that are trying to destroy your vehicles. Infrastructure. If you have power failures and you need to send them out to do scouting, you may want to send out unmanned vehicles to scout the lines, use image classification to determine if there is a fault, what type of fault it is, so that you can dispatch a repair crew. Drone journalism is becoming a fairly popular topic now, and in many countries, drone-based journalism is not welcome, and it's possible that they will actually try to destroy the drones when you send them out. So covering large areas with a number of drones to try to capture imagery is certainly a good strategy. And agriculture. Certain crops, such as coffee, for example, does not grow uniformly when it's planted. In fact, it will actually start to mature in random patches throughout the fields. And so, if you have a very large agricultural area, being able to do search of that area and do it efficiently is of use. So you may ask, well, what's the risk of sending out drones to look at coffee? Certainly weather is always a risk in any of these situations. There are certainly examples of birds and other animals that don't like drones flying in the area. They will swoop down and attack them and most likely destroy them or just knock them down. You may not be able to recover them for a while because they're very far out. There's been examples of just mechanical failure during operation, especially with these lower cost platforms. You're trading off quality, you're trading off mean time first failure. So it's certainly an issue. And finally, some people just don't like the idea of things flying around looking at things on their property or near their property. So certainly in a military context, you may even have civilians that are just quite willing to take pot shots at things just for either their own amusement or the belief that you're doing them some harm. So I'm going to talk a little bit more about the actual finding problem definition. So really have is this set of tasks that you want to complete with what we think is one of the differentiating factors being that a task is getting to the location, performing collection, and returning to the base with that information. We're assuming that there are no communication capabilities in this situation that will allow you to send what you collected over the network. You have a set of locations that correlate with those tasks. It's just a one-to-one correlation with this work. And it's really just a complete graph. We assume it to be plain, fully connected, complete graph of distances. All you need. So we can define a path, and so the probability of survival for an agent is really just a function on the edges that it's traveling over. And in our case, we say there's a fixed probability of survival per unit distance traveled on an edge. So we totally agree it's a very simple quantification of risk. There are certainly many other ways we could look at risk, but we try to keep it as simple as possible, mainly for the sake of exposition. And finally, your asset itself also has value. You're not only losing on the things you're trying to collect, but you're also losing out on the value of the asset that you're sending out. In the hunter example, you're using the life of one of your skilled hunters. When you're talking about these unmanned vehicles, we're entering an interesting age where we can actually look at the trade-off between losing our assets and what we gain from using our assets. So I think certainly the operations research people are chomping at the bit to be able to do very large-scale operations where everything is just a trade-off of cost. What it's costing us to do, what we're risking as far as cost of time and money, and what we're hoping to gain. Now, that of course requires that you have some transferable utility between the task values and the asset values. That's not something I'll talk about here, but certainly a strong assumption. So just to show one of the interesting properties of this, consider a unit circle of 1 kilometer. We'll assume that the probability of failure over this 1 kilometer distance is 5%. And so the question is, UAV will go out and collect on tasks in sequence, and the question is, when should it come home? So we look at, theta here is the asset value once again, where the top line is value 1, 2, 3, and 4 going down. When the value is 1, your best option is to collect out 5 out of the 6 and then return home. As the value of the asset increases, you go down to 4, 3, and finally, at asset value 4, your best bet is to never leave home at all. Don't collect any of the tasks. So now, extending this to the multi-agent case, it's really a simple matter of just adding up the expected value of all of the agents. Now, what makes this a little different is that we're not assuming you know how many agents need to be sent. We're assuming that you have, in some sense, an inexhaustible supply of these. They're low cost, you can manufacture them very quickly. And the question isn't how to best optimize for how many you have known ahead of time, but rather how many do you send and where do you send them? And so there are multiple different kinds of optimization problems going on. So going to the multi-agent case, we can once again see kind of interesting effects of changing the asset value. In the base case, when assets were nothing, which is really a kind of trivial sort of case, it's always the best policy to send one to every single task. And that's because you're minimizing the distance needed for that single task and maximizing the probability for each individual task. And so if you have 100 tasks, for example, when the asset value is 0, your best bet is to send out 100 agents and dispatch one to each of the tasks. As we get to one value platform, this is when it's not worth sending out to some of the tasks on the fringe. This is important because, especially in a military context, you often get requests from a lot of different sources for gathering information. You may be the one who runs the piloting of this asset. You get all different organizations that are submitting you tasks. And they may not understand the risks involved. And so there are going to be cases when you say, listen, you wanted us to collect on this, but it's not worth risking our asset because the risk is very high at this time. And then as you get to the medium value, this policy becomes just to send out one of these agents to collect on 2 of these tasks to minimize the risk of what you're going to lose. And then finally, at 3, the high value, once again, your best bet is to send nothing anywhere and just wait. So what we see is, from our understanding, there are really 3 key properties of this that make it interesting. First being attrition, the idea that you're losing these platforms and anything you plan for them to do if the actual event of being lost is realized. You're trying to maximize the value of both the tasks that are completed while also trying to minimize the loss of assets. And then finally, you don't provide a bound on exactly how many vehicles you want to use, unlike many of the multi-agent types of problems. So to solve this, we actually went with a clustering approach. Once again, not from the planning community, so I went with something I knew well. But really, in general, we saw a couple things that we observed of solutions. We ran some brute force solvers for smaller problems and really observed what we saw in solutions. No surprise, solutions will often prefer tasks that are closer to the base because there's just less risk. You don't have to go out as far to get to them. As your asset value increases, it decreases your willingness to go out that far and collect on those tasks. But importantly, we saw that tasks that are very close together, if you consider them right on top of each other, their value can be combined because there's zero distance in travel between them. So even when they're very close, that value can often be aggregated into a single value or a single cluster. You can evaluate by itself to decide if it's worth going out and collect. And then finally, as the distance from the base increases, what you need are larger, higher density clusters to actually be worth going out to collect on those groupings very far away. So collaborative hierarchical clustering we chose because of the dynamic nature of this problem. As we increase for differing asset values, differing risk values, you may want to only generate clusters that are very close. You may also, in other situations, want clusters that are far away and larger. And so we wanted to find a solution that would handle any of these cases for any set of parameters. So in this case, what we do is for the hierarchical clustering is you actually, each individual task starts out as a cluster on its own, and you iteratively combine these clusters pairwise. And so in this case, the blue, green, and red are the first pairwise clusters that were created. And then the green and red cluster join together to form a single cluster at the next step. In general, they do this often using just distance in the space, measured distance, which can be measured in any number of ways. And so in our case, we actually normalized distance to be the gain and expected value for merging those two clusters. And I'll talk a little bit about why that is somewhat challenging. So the properties of a cluster are really, you can characterize with only a few different labels, if you will. First is the value of the tasks in that cluster, the distance needed to visit all of the tasks in that cluster, and then finally the distance from the base, how far you need to go, in some sense twice, to get out of that cluster and back before that cluster. One of the challenges is that computing the optimal intertask distance as well as the distance to the base is really solving a small travel and sales window. And we need to evaluate this value every single time we want to evaluate a merge between any possible cluster in the space or even the singleton cluster when we start out the problem. And because we were scaling up to 2,000 tasks, performing even very small TSPs at a very, very fast rate very quickly became feasible. So that actually may be something we could get some intuition on if there are good solution concepts for very small TSPs. Because in general, these clusters don't usually exceed 10 tasks. So what we did is we came up with an approximate method. Instead of representing the clusters by their shortest path, we instead used the minimum spanning tree as a structure to determine the amount of distance between them, which we know is at worst twice as bad as the traveling salesman solution. And then the base distance was really just the distance from the base to the closest task within that cluster. So what we have here is the SG, the sequential greedy algorithm. This is actually a version of the CPPA, which is the consensus-based bundle algorithm. It's the equivalent centralized version of that. But unfortunately, that was not very well suited to this problem, so we actually made some tweaks to make sure it only merged on things that provided a gain with expected value. So the orange line is the original, the blue line above it is the tweak we made to make it a little more of a fair comparison. The green line is our clustering algorithm with approximation, and the purple line on top is the exact clustering method. This actually computed shortest path for every single cluster as a merge evaluation process. So, in the x-axis, we increase the asset value. Once you get out to close to 8 or 9 asset value, you get very close to the point where it's almost never worth sending anything out anywhere at all. So, that's why you see values that are very close to 0. And so, part of this evaluation here was just to show ourselves that our approximation wasn't too far off from the exact. We weren't doing massively worse. And we're also providing gain over the only other solution we had at the time. This is scalability. We tried it for 100, 500, 1,000, and 2,000 tasks. And in this case, we're just showing the percent improvement over the sequential baseline. So as we get more tasks, our performance improves. And this is the time cost, where there's sequentially there. Cost decreases as the problem size increases because you're narrowing down things that you would actually consider. Clearly, our precise method is very, very time consuming, and the approximation does very well. So, what we're looking for are really collaborators, people who can help us frame this problem, formalize it, look for other solution concepts. Very interested in revised threat models that you have actual threats at locations that are providing a radius of danger. And finally, what we think is really interesting is starting to exploit the properties of digital goods rather than picking up packages and delivering them somewhere. These are things that can be gathered by multiple agents at different times, which allows for redundancy of collection to mitigate risk, and allows you to actually communicate these pieces of data through possibly a mobile ad hoc network, which has a number of interesting properties, such as how do you diffuse that information through the network where some of your nodes may have limited storage. And finally, just even more complex problem. If you do a collection, does it actually create information about other collections that can be done? That's all I have.
So it seems that what you really solving is an optimization problem.
Thank you. So it seems like what you're solving is actually an optimization, a stochastic optimization problem. And it seems like an obvious tool would be part of decision processes, MDPs. Not MDPs for planning, but MDPs for optimization. And then it also seems that don't really care about risk, don't care about expected utility, and that's that.
So yeah, we had actually, for the single agent case, implemented a simple MVP, actually for that circle case, just to show that it had the same results. I'm not clear how you extend that to the multi-agent.
It's just that you have more actions. It's still a single MVP. It's not I just don't see the reason for going for 10 MVPs. Yeah. There's no decoupling there.
Okay. Yeah, that might be.
You have the central controller, right, that controls all the agents.
Do actually our follow-on work to this that we're working on now is a decentralized version of this deception and government comms. So how would you decentralize control yourself?
Yeah. Mike.
I'm sorry. So yeah, I think decentralized is certainly the goal of this work, but having a centralized solver that can provide very, very good results is always going to be the baseline. So I think that's certainly of interest.
But what I want to distinguish is, following up on Guy's comments, is that there's a difference between doing something decentralized and planning in a centralized fashion. In this case, it seems, even if, what would be the centralized case here? Would you have the agent decide on their own if they want to collect stuff? It's not obvious to the extent. In which direction you take it?
Yeah, I think the decentralized is more applicable when you have dynamics in the environment. You don't have the ability to communicate back to a centralized plan. That also, and this actually relates to the last speaker, starts to hit on communication issues. Now you have a decentralized planner with limited range of communication and possibly losing communications. It makes for a very interesting and complex problem. But yeah, MVP is certainly a good place to start.
Just a small point on this. How would you do an MVP with an unbounded set of agents, which is essentially the big problem that we're having here? That we can have, as you said, there was an unbounded set of agents, and I don't see how you could do that with it.
I think if you bound the maximum number of agents.
So we can have a maximum. That's fine.
Yeah, that's true. We assume that you're not going to have more agents than tasks, but once you get into the redundant collection, you might have more agents.
How would you do a depth MVP with an unbounded number of agents? How would you do a depth MVP with an unbounded number of agents? I mean, this issue of unbounded number of agents would be a problem if you went to a decentralized solution or you stayed with a centralized solution. Okay, Larry, very shortly.
Okay. So I'll just say this. To me, this looks very similar to vehicle routing with time windows. And the techniques that work there are basically
local search techniques.
And we're kind of looking for a set of paths, and you don't really worry about who's going to do them. So we can talk offline.
Yeah, if people didn't know how the time windows work, probably.
It's not exactly time windows, but the structure is. Price delay.
Yeah.
Okay, thank you very much.
Thank you.
Okay, the last talk in this session is the formal analysis of required cooperation between Islami, Pakistan, Haran, and Ramabadi. How did you manage to, Jeff, how did you manage to move the different strengths?
Good afternoon, everyone. My name is Sharat Sridharan, and I'll be presenting now a formal analysis of required cooperation in multi-agent planning. So this is a joint work between Dr. Yusha, myself, and Dr. CPPAR Definition. Unfortunately, the other two will make it to the conference, so I'm presenting on their behalf. So we will begin our this presentation by looking at the set of all possible multi-agent planning problems. Let's assume that this blue box kind of represents that set. And now we will start looking at unique problems from this set. And this being ICAPS, we start with a multi-agent form block split. So this is like a simple extension on the classical block split problem, where here in fact you have multiple robots that are trying to arrange blocks in some specific manner to get some specific configuration. If one way to look at this specific problem, what we'll see is you don't actually require multiple robots to achieve the goal for this problem. But just the presence of these multiple robots can help boost the efficiency of how you can solve this problem. But on the other hand, if you were to move to say a domain like logistic domain, where you have multiple types of agents. So in logistic domain, you have these truck agents that can move from one part of the city to another, and you have these plane agents that can move from one city to another. So there are problems in this domain that cannot be solved by a single agent. So this allows us to define a subset of multi-agent problems where you actually require multiple agents to solve the entire problem. So we'll call these problems as required cooperation problems or RC problems. If we look at the logistic domain, the reason why we needed multiple agents is because we had these different types of agents. So one might assume this requirement for cooperation might arise from this heterogeneity of the different agents within the problem. But if you were to look at a different problem like this burglary problem, where you have agents of the same type, and the goal of this problem being you're trying to steal this diamond, and just the act of removing the diamond from the pedestal causes the doors to the room to actually get closed. And if you want to completely solve this problem, that means getting out of the room. So unless you're Indiana Jones, you will require multiple agents to solve this problem. So we can in fact take this set of RC problems and divide it into two types. There is a type 1 problem which are only consisting of homogeneous agents, and you have this type 2 which consists of problems with different types of agents. So basically we've here seen three categories of map problems. One which can be solved by a single agent, one which requires cooperation but consists of multiple types of agents, and one where it requires cooperation but only consists of the same kind of fields. So the question would be, why do we care about this categorization? One important reason is these properties could actually help in deciding what kind of planning algorithms would go on to create solutions for these kind of problems. For example, if we are considering centralized planners, one could solve the first type of problem by using a single agent, and then just use a post-processing step to you can expand it to use multiple agents. Similarly, for the second kind, if we were to assume the existence of this transformer agent, which is this flying truck, if you assume such an agent would exist, we could have solved that problem using a single agent. And we could have then used a similar post-processing step to separate it into existing different agents. While the third problem actually requires you to use like a normal multi-agent planner where it considers all the agents. Now, the second reason why one would require this is when you are creating benchmarks for multi-agent planning problems, you would want problems from each type. So if you were to look at the last OD map competition, we would see that most of the problems which required cooperation actually ended up being in the small region in type 2, which in this work we will call it DBC, and you will see DBC RC, and you will see later what that means. So it doesn't actually there have been problems from the entire spectrum of possible RC problems, and while we are creating benchmark, this is something we would require. Okay, now in this work we've been asking ourselves these three main questions. One, what conditions would actually require a problem to have like RC? That is, under what condition is multiple agents actually required to solve the problem? The second, how does these conditions actually affect planning for multi-agent problems? Are there some certain subsets of multi-agent problems that can be solved easier than the rest? And finally, can we actually provide, these were some certain subsets of multi-agent problems, can we provide an upper bound on the number of agents? Now, this is going to be the outline of my talk. I'm going to start with the formal definition of what required cooperation means. Then we look at how we are actually dividing problems into two types. So like I mentioned, it's heterogeneous and homogeneous. So we need a way of identifying what problems actually consists of heterogeneous agents. Then we'll take a look at each of these types. Type 1, what are the causes of RC? Under what conditions can we say that this is a single agent solving the problem? And can we provide some kind of upper bound on the number of agents? For type 2, we introduce this concept of transformer agents and also suggest or propose this centralized multi-agent planner called RC plan, which makes use of this idea of transformer agent to simplify planning for these type 2 problems. Now, moving on, we'll start with the RC definition. So we define multi-agent problems by actually extending the normal Sackler formalism, where we define the multi-agent problem using the double V, phi, and G, where phi is a set of agents, and we have this additional assumption that now the goals are actually independent of agents. So the goals do not consider continuous agent variables. Okay, so we will say that for a given multi-agent problem P, we will say that the problem is K agent solvable if we can come up with a subset of K agents that can actually solve the problem. And the problem is said to have RC when it's not a one agent solvable problem. Which means there isn't a single agent you can use to solve the entire problem. Okay, now moving on to the problem types. Like I mentioned, we broadly divide the entire set of RC problems into two types, type 1 and type 2. And we do, so like we mentioned, type 2 consists of only problems with heterogeneous agents, and type 1 consists of problems with only homogeneous agents. And we define this concept of heterogeneity using these two new ideas called action signature and variable signature. So while defining things like the capabilities of the agent, you can just directly use the agent actions. The problem being, if you look at two agents, their action list will be maybe unique because the grounded action will contain like agent name. So we come up with this action signature where we take the list of grounded actions and replace just the agent name with a global agent symbol. Similarly, we define this concept of variable signature, where we replace agent name and agent variables with this global symbol. Now, we say a given multi-agent problem has heterogeneity if it satisfies one of these properties. If it has domain heterogeneity, where two agents have similar variables, but their domain is different. For example, in logistic domain, let's say truck and plane has this fuel variables, but the actual fuel value could be different for both agents. We will say the agents have variable heterogeneity when certain agents have some variables that the other agent don't, like altitude for planes, which is not there in truck. We say the agents have capability heterogeneity when certain agents can do certain actions that the other agents can't. Like truck can drive while plane can only fly. Something like that. So we basically call this agent heterogeneity as BBC, because this is the three types of heterogeneity that it can show. Now, moving on, we'll start with the first type of problems, namely type 1. And like I mentioned, type 1 consists of problems with the same type of agents. So what could be one possible reason for required cooperation in such problems? So one quite possible reason is when the state space of the problem itself is not traversable. An easy example is if the agent has some kind of non-renewable energy, say it has a battery that will run out automatically. So it will require the help of other agents to complete the problem. So we analyze this idea of state space traversability through causal graphs. In fact, we use a variation on causal graphs which we call ICGS, or individual causal graph signature, where we replace these variables with agent variable signatures. So whenever there are agent variables in the causal graph, we replace them with variable signatures. So, and we now define these two new concepts, inner closure and outer closure. So for a given causal graph, an inner closure refers to set of variables that are not connected to any other variable through undirected graph. So these basically represents a set of variables that gets updated together by maybe by the same action or something. So for the outer closure, they refer to those variables which appear in trivial conditions for these inner closure variables, for the actions related to these inner closure variables. Now, we say a given causal graph, so a given inner closure is locally traversable if for any two values of IC, we can come up with a plan that connects them. And the causal graph itself is traversable if all the inner closure are locally traversable. So, the very obvious question is, if you know that a given causal graph is actually completely traversable, does that mean it does not require RC? So, can we say for sure that a single agent can now completely solve the problem? Well, not exactly. If you go back to the burglary problem, and if you look at the causal graph of this problem, you will see that there is only a single inner closure, and it is locally traversable. Unfortunately, as we've seen before, it does require multiple agents. So what's going on here? So the basic idea is here we have a causal loop, and we find out that whenever there are causal loops in the causal graph, that can also require cause you to require cooperation between agents. So this brings us to our first theorem that we proved on our paper, which basically says that if a given problem has a causal graph which is traversable and contains no causal loops, then we can be sure that a single agent can be used to completely solve the problem. So now what about the rest of the problem that actually requires? Can we give somehow an upper bound to the number of agents required? So in these cases, what we basically want to do is we want to break these causal loops. So this causal graph, if we assume that the reason of the causal loop is because of this walk-through action. So basically, once you take the diagram, it causes the door to close, and now you can't walk through or update your location because the door is locked. But if we had one more agent, the walk-through action is no longer constrained on the door lock, because you can have the second agent open the door. So basically, what we found out is this upper bound on the number of agents required is actually equal to the product of the domain of each of the variable signature associated to the causal loop. So now, finally we come to the last type, type 2. And here we have mainly going to talk about two concepts, the transformation and the planner which makes use of this concept. So, like we discussed, these problems, type 2 consists of problems where there are heterogeneous agents. But an important thing to remember is, just because there are heterogeneous agents doesn't mean that it requires RC. Nor does it mean that whenever it requires RC, it's caused due to these heterogeneous agents. Because any of the points we talked on the last section could always lead to required cooperation. So in this section, we actually only focus on the smaller part of type 2, which we call DBC-RC, where we know the problem is RC, and the causal graph itself is traversable and does not contain any causal groups. So that means the reason for required cooperation is because of the different natures of the agents, like the heterogeneity of agents. Okay, so basically we define this idea of this new virtual agent which we call transform agent, which is basically this agent which can perform any of the action of these single agents. So in our previous example, it was this flying track which could go both on the road and actually fly from one airport to the other. And we also define this concept of connectivity graph. There is a graph consisting of each agent, and there is an edge between the agent whenever their state space actually intersect at some point. And we were able to show that for a given problem, if the connectivity graph is completely connected, then the entire problem can be solved by using a transformer. So for example, if you look at a logistic problem where there is only one track engine and one plane, and they meet at this airport, we can come up with a plan where we have this flying truck which moves from one part of the city to the airport, and then from that airport to some other part, and like to unload some packages. So we can use this transform agent to solve the entire problem. Now, similarly, we can also show that given a transform agent plan, we can compile it back into their individual component, individual agents. This is kind of trivial because we know all the actions done by these transform agents, their actions of their individual components. So one example would be, in this case, we have a flying track which goes from one part of the city to the airport, and it goes from this airport to another airport and drops off the package here. This can now be turned into a plan where there is a truck moving from one part of the city to another, and then a plane actually picks up, like the truck drops the package at the airport, the plane picks up the package and moves to the other airport and drops the package there. Now this finally brings us to the plan we have proposed here, which basically makes, I'll make it quick. So we basically designed this planner mainly solve the DBC-RC problem, and our intuition here is, when compared to a normal multi-agent, a centralized multi-agent planner, you are actually, while the centralized multi-agent plan is considering actions of each individual agent, we only need to consider action of this one transformation problem. So if you look at the domain like Zero Travel with 6 agents, the number of instantiated action for RC plan is only around 9K, while for a planner like MapLab it's 54K. So what we did is we tested our planner on 11 out of 12 coding map problems. We couldn't test it on wireless domain because it didn't meet one of our assumptions. And we compared it against MapLab, which was this compilation-based method which did quite well in the coding map competition. And we found that we did better than them on the coding map problems in 2 out of 3 criterions. And also the fact that we did so well on the coverage means that most of these problems are in fact belongs to that small group we mainly designed our planner to work on. And like we expected, as we moved on to larger problems where there are more agents, we ended up doing much better. So finally, in conclusion, we've here introduced the concept of required cooperation. We provided a way of formalizing this and tried to find out conditions where required cooperation can appear for different kinds of problems. And we've basically proposed a planner which makes use, a centralized multi-agent planner, which makes use of this concept to improve planning performance in multi-agent problems. And we've also found out coincidentally that most of the current multi-agent benchmarks, like for the unfactored problems in CPPAR actually only covers a small subset of possible multi-agent problems. And that's our work. Now, we're optimists.
Questions?
Did you do any analysis of the specific competition domains to see which ones require collaboration and which ones don't? Because I believe that some of them really don't require any collaboration, single agent and so on.
We haven't done that. We have the data, but we haven't quite looked into the data as to see which one actually has made use of all the types of agent types. But one thing we found out is even when there was required cooperation, it was mainly because all of the agents didn't have the capability to finish the problem itself. It was not because of something like, say, stage-based diversity or things like that. So that was something we found.
It would be also interesting if you can design new domains to fit the other classes.
Right, that's exactly that's we are hoping that will be our next step. So we are trying to look at that direction.
Any more questions? Can you go back to the experimental results? So over here, when you use these transformer agents, the planner you're comparing with, I mean, the idea behind the coding map competition was also part of it was privacy, right? So I don't know whether this specific planner used it, but they have a disadvantage in that they have less information.
Yeah, so one of the ways that map updating ensures privacy is by making sure that each agent is only using its own private objects and private actions. And this is something we actually ensure during our expansion step. So when we have this transformer agent actions and we are trying to convert it into single agent actions, we will make sure that these actions are only operating on its private objects and wouldn't probably use another agent's private object or things like that. So we believe that we are also ensuring the same level of privacy that map will.
Okay, and the theorem you showed about when you can use a transformer agent, so when you talk about connected space, this wouldn't work if you had resources that were non-replenishable, right?
Yes.
Okay, any other questions?